plus. So let's start with some very basic question. So these are, suppose these are NP optimization problems. So these are optimization problems for which you can assess the value of a solution efficiently. And now, okay, so so these are the kind of optimization problems that we can hope to solve. And so what do we know about them? So we, for some of them, we know, efficient algorithms to solve them. So those are, tractable optimization problems. We can get, we know how to get some guarantees for the problem in polynomial time. And on the other hand, we know that certain kind of guarantees for problems are hard to get. Under very plausible assumptions, there's no polynomial time algorithm. So those are intractable problems. And then, for most problems, there's a range where we don't know, if the guarantee is if you can achieve it in polynomial time, or if it requires, exponential time to achieve the guarantees. And we don't know if it's tractable or intractable. And so the general goal of this kind of research is to figure out sort of what's the dividing line between tractable optimization tasks and intractable optimization tasks. And sort of the goal is to understand the principles that distinguish tractable from intractable problems. I'd also like to so to motivate kind of things we're looking at. So I'd also like to look a little bit in sort of the difference between theory and practice of algorithms for these kind of problems. So in theory, we care about the guarantees that we can prove about the algorithms, and so we want these guarantees to be as strong as possible. And we sort of we don't really care how the algorithm looks like. We try to exploit as much structure in the problem as possible. So the algorithms tend to be very complicated and try to and very specific to the problem. And in practice, like you only care that you have a pragmatic mindset. You don't care so much about the guarantees. You just want that it works well. And but there's another surprising thing that in some sense many of the algorithms that are used there are not that specific to the problem, but instead they come from a rather they come from a general meta from one of a few general meta algorithms. And meta algorithms are algorithms that are not tailored toward a particular problem, but they instead apply to a wide range of problems in the same way. And examples for these kind of problems are gradient descent or this expectation maximization. And belief propagation, set solvers, all these kind of algorithms, and they tend to have, at heart, they are based on local search. These kind of algorithms, and it's very hard to prove strong guarantees about them. And typically, you sort of need to start from a solution that is already pretty close to the solution, to the kind of to a good solution, in order to show that these algorithms converge to a good solution, and but they have the advantage that you can apply them to you can change the problem a little bit and they apply still in the same way to the problem. Okay, so that's something that is nice about meta algorithms, and so the kind of something this meta algorithm is something that is very appealing also from a theoretical point of view, and so that's the question. So here the question is, could you have some kind of theory that distinguishes between tractable and intractable problem that is based on a meta algorithm, and it would have to be because we want these strong guarantees, it would have to be a non-local meta algorithm, and but it would still have this property that you can apply to a wide range of problems in the same way. And the hope is that this meta algorithm is able to distinguish between tractable and intractable problems in the sense that that this meta algorithm gets the best possible guarantees for these kind of problems among all efficient algorithms. So it means that either so if there exists a meta algorithm with this property, then either the meta algorithm is able to solve the problem, or we know it's intractable. So that's the question. And so that if this kind of meta algorithm would allow you to complete this picture of this landscape between tractable and intractable problems. Now, okay, so this sounds like a very implausible kind of scenario. That there's this this kind of single algorithm, and it can it can help you to distinguish between tractable and intractable problems. But it turns out that there are two developments that really give hope that such a such a meta algorithm might exist, and that you can reason say reasonable things about regarding they kind of unified theory. And these two developments are Unigame's conjecture and the sum of squares method. And together, I think they give new and useful ways to think about algorithm design in general. Okay. So that's sort of the basic motivation for this talk, and trying to explain these things. Yes, so I should also say, the kind of granularity at which we are working. So, for the problems that we consider, there will be some focus on worst-case problems. Just because we also have in mind of proving hardness results, and it's very hard to prove hardness results for non-worst-case problems. But in some sense, the algorithms that we will consider, they will be able to exploit, specific properties of your instances, and they in some cases, they will have better guarantees for nice instances, which is something that is desirable. So in some sense, like for the kind of problems that we look at, it's very flexible, but the more severe condition is that so the kind of algorithms that we look at, they will not focus on practical efficiency. We will really only focus on this difference between trying to distinguish tractable problems from intractable problems. Okay, so which means that if the algorithm runs in time n to the 100, it's tractable, and we don't have to think about it anymore. But I think that it sort of would miss the point of if you're only interested in practical algorithms, then it would I think be sort of premature to disregard these kind of algorithms, because the proofs that these algorithms, that an n to the 100 algorithm works, it has to give insights. It will give insights into the structure of the problem, and these insights in turn can lead to algorithms that are better in practice. There are many examples where algorithms that are not useful in practice turn into algorithms that are useful in practice by tuning them. And so just a different picture of what I just said. So we will operate sort of in this kind of space. So algorithms that are maybe slow in practice, still polynomial time, but they have very strong guarantees. And maybe some of the talks yesterday sort of stressed this point. We want algorithms that are fast in practice, and you sort of make the assumptions that you need in order to say that the algorithm works. And but I think the ultimate goal should be algorithms are both fast in practice and have strong guarantees. And it seems useful to sort of start from both perspectives in order to get to this final goal. So now let me explain what's the Unigame's conjecture about. And so at the heart of this problem is the following graph theoretic problem. Which I call small set expansion, and it has some parameter epsilon. Okay, so what is this problem? So you're given a graph with n vertices, and it comes with the promise that there exists a set in the graph of size delta n, where delta n is a pretty small constant, and this set has expansion at most epsilon. And so and the epsilon is maybe you can think of it as 0.01 or 0.001 or something like that. And so the expansion of a set of vertices in a graph is the probability that a random step starting from this set leaves goes out of the set. So if a set has small expansion, it means that most of the edges that touch the set stay inside the set. So you have a graph like that, and your goal is to find a small vertex set that has small expansion, but you're allowed to lose, in some sense, quite a lot in terms of the expansion, but you want it to be small. Okay. So that's the problem, and so there's the graph version of the unique games conjecture asserts that for every positive constant epsilon, this problem is NP hard to solve. Okay, and this is not the original version of the unique games conjecture, but for the purposes of this talk, it will be will be good enough to think about this problem. And maybe let me just explain a little bit what's the difference in the original version of the problem. So in the original version of the problem, this graph, it comes structured in a particular way. It means in particular it has the vertices come partitioned into sets of size 1 over delta. Okay. So constant size sets, but of size 1 over delta. And so if instead of talking about arbitrary vertices of size delta n, you look at very particular vertex sets of size delta n. That are structured in the following way. They intersect each of these parts of the partition exactly once. Okay, notice that these, if the vertex set is partitioned into sets of size 1 over delta, and if you intersect each of these sets exactly once, then you have, you pick, then the size of the set will be delta times the number of vertices in the graph. Okay. It means that you, somehow here in this structured version, like you're restricting yourself to particular kind of small sets.
Sorry, I didn't catch this. So, this small set expansion conjecture, you're doing something new out of it?
No, nothing new.
But in some sense, you don't need just focus on small set expansion, right?
Yes.
You're just trying to.
What's the structured thing? That's what.
No, that's the original version. That's the constraint satisfaction version of the unique games conjecture.
That's what. That's
yeah, lifts of graphs. Yes.
Okay, fine.
But yeah, I mean, we will not. I mean, if it's gray, you don't have to worry about it.
Oh, okay. Now I understand.
In the original version, what was the guarantee and what was the?
Yeah, exactly. Yeah, exactly. So in both the promise and the goal, you wanted these structured set. So you have a promise that there exists this set that intersects each of the parts exactly once, and it has expansion epsilon. And your goal was also to find such a set that intersects each part exactly once and has expansion at most, let's say 1 over 10. And because sort of this restriction comes both in the promise and in the goal, a priori this problem is incomparable to the unstructured version. But it turns out that actually this problem is only easier. So it means that if this graph version of the unique games conjecture is true, then also the original version of the unique games conjecture is true, and that will be in some sense good enough for the purposes of this talk. Okay. Now, why is this unique games conjecture interesting? The reason why it's interesting is that it has because it has really it has these really surprising predictions that I alluded to in the first couple of slides. In particular, it predicts that for a wide range of problems, and these problems, they are really different. In some sense, before they looked almost unrelated to each other, but still for this wide range of problems, if the unique games conjecture is true, then it's NP hard to beat the current best approximation guarantee. The current best approximation guarantees. So the approximation guarantees of the current best algorithms. Okay, what this means is that in this picture, where we sort of have this gap between what we know to be tractable and what we know to be intractable, if the unique games conjecture is true, then this prediction means that in some sense everything here that we didn't know about is actually intractable, and sort of only this part that we already knew to be tractable is actually tractable. But there's also in some sense, as part of this work on, okay, so this is work, many people, starting with Subhash Code, and this kind of implication is to Raghavendra, and like a key insight that goes into these predictions is actually that that the current algorithms for these seemingly unrelated problems, they can actually be captured by a concrete and rather simple meta-algorithm based on semi-definite programming.
David, I realize that this is only a cartoon, but
yes.
In this picture, where would the graph isomorphism, for example, where it's...
So we started with NP optimization problems,
Yeah,
and
think of the variations.
yes.
Right, the Tau optimization problem.
Yes. I mean, it's a cartoon. I mean, I think most people. That work on graph isomorphism, they would think that it's actually tractable. But yeah, we don't know it's tractable.
What they would think?
That it's tractable?
Tractable, yes.
Yeah.
So sub-exponential for you is already tractable?
No, not really. So yeah, that's also a good question. What does it really mean to be tractable or intractable? And yeah, we'll discuss this later. But yeah, so I think here the focus is really on optimization problems where it's about approximation, and
but more specifically for constraint satisfaction problems.
Yes, so yeah, for constraint satisfaction problem, this would not be a cartoon. This would just be the truth.
So the ball is not supposed to capture all computational problems on Earth, but a large class of them that includes all constraint satisfaction problems and also some other problems.
To capture everything that's there.
But I mean, I think that's really the cartoon. But I think this. At this point, that these problems, it's not that they are, a priori, very similar to each other, and it's just, and so the algorithms are all similar, and it's just sort of vacuously true that, if you can show hardness for one problem, then, all the other problems are equally hard. But they're really, different, and like just to contrast the current state of affairs is that, even if you understand one problem very well and you now change it a little bit, it might be that both your algorithm goes away and your hardness results go away, and it's something. There's a very big contrast to the kind of things that we know. The things that we know are really sort of very isolated kind of points where we know things are tractable or things are intractable. And so I will. The next couple of slides, I will explain what this meta-algorithm is doing, but we should keep in the back of our minds that one question is whether this conjecture is really true. Okay, because these predictions only hold if the conjecture is true. And why could what are sort of questions that you might sort of ask when you're trying to understand whether the conjecture is true? One question is, maybe there are more general meta-algorithms, and that are, because here, the Unique conjecture really identifies a very particular, concrete meta-algorithm, and it could just be that there are other meta-algorithms, and for some problem they are, they get better guarantees, and in this way, would refute the Unique conjecture. And it turns out that there are, more general meta-algorithms. But it also turns out that most of them, they actually cannot, refute the Unique conjecture. It means that, we know instances where, these more general meta-algorithms, they, don't get better guarantees than the simple meta-algorithm. But there's one exception, and this exception is called the sum of squares meta-algorithm. And not only is it the case that we don't know an instances where this algorithm fails, but we know more. We know that this particular algorithm, it works on all of these instances that that we know on all these constructions of instances where we know that the other algorithms fail. So that will be that was a preview to what we will discuss next. Yes. So just different way of saying things. So if the Unique conjecture is true, then it really means extremely strong. It would imply an extremely, it would sort of boost. It would be a quantum leap in our understanding of this complexity landscape for these optimization problems. And on the other hand, the connection between the Inner-Games conjecture and these other problems, it really seems rather tight. So if you come up with an algorithm that refutes the Inner-Games conjecture, it's quite plausible that this algorithm also would lead to improved algorithms for many other problems. But this is not a formal implication. So there's no equivalence between sort of getting better algorithms for a wide range of problems and the refutation of the Inner-Games conjecture. Okay, so now so before explaining this Inner-Games the meta algorithm that underlies the Inner-Games conjecture, let me sort of start talking about something very general, which will be useful for the rest of the talk. And these are functions on the hypercube. Okay, and so a function on the hypercube is just a function that takes an n-bit string, and let's say we encode the bits as +1 and -1, and it outputs a real number. Okay. And it turns out that even though this object looks very unstructured and sort of almost random, these things are surprisingly useful for thinking about problems, algorithms, and proofs. So one example where this kind of functions are useful is for maxcut. Okay, so the maxcut is you're given a graph, and you're supposed you're trying to find a bipartition of the vertex set such that as many edges as possible cross the bipartition. And, it turns out that we can think of maxcut as just the a problem of trying to find the maximum of a function on the hypercube. So how can we do this? So just so if you have a bipartition, okay. So think of having variables x1 up to xn, one variable for each vertex, and think of assigning, if you have a bipartition of the vertex set, think of assigning -1 to the vertices on the left of the bipartition and +1 to the vertices on the other side of the bipartition. Okay. And so in this way, you encode every possible bipartition of the graph as a bit string, and then trying to find the best bipartition is just same as trying to find the maximizer of this function on the hypercube. It assigns for a point x the number of the fraction of edges of the graph that are cut by the bipartition x. And then this function is sometimes called the Laplacian of the graph. Now, one very useful fact about functions on the hypercube is that there's a nice representation for them. There's nice orthogonal basis for these functions, and it corresponds to if you write function in this basis, then you represent the function f as a multilinear polynomial in the variables x1 up to xn. Okay. This is also the Fourier basis of underlying. Now, okay, so let's see an example. So, for example, this function that assigns x, to x the fraction of edges cut by the bipartition of x, you can, write it as a quadratic polynomial in this way. And now here, it doesn't look multilinear at first because we are squaring here these things, but because on the hypercube, xi squared is equal to 1 always. And so it means that this polynomial here over the hypercube is the same as this. Okay, now you have a multilinear polynomial. Here you have a constant term, and here you have multilinear quadratic terms. Now, okay, just as a sanity check, this is the number of multilinear monomials is 2 to the n, which also happens to be the dimension of the of functions of the space of functions of this type. So it means that really there's like a unique way of representing every such function as a multilinear polynomial. Now there are two notions that are useful in terms of in this context. One is the notion of degree. So the degree of a function on the hypercube is just the largest degree of a term in its multilinear representation. And if we look at this guy here, then we see that its degree is 2. And another useful concept is also of a junta. So d junta is a function that depends on at most d variables. And that's equivalent to saying that the variables, that there are at most d different variables that appear in the multilinear representation of the function. Okay. And for example, this the function we're interested in for maxcut, it's a sum of non-negative 2 juntas. Okay. So if you look at in this way, it's so maybe not clear how to see it. But if you look at the function in this representation, you see that it's a sum, and these here, these functions here, they just depend on 2 variables, so it's a 2 junta. And you see that these functions here, they take only non-negative values. Okay. That means that this here is a sum of non-negative 2 juntas. Okay. So now what is this? Now let me explain this meta-algorithm that underlies the Nigam's conjecture. And let's keep this example of maxcut. So we are trying to maximize this function over the hypercube. And usually, if you think about these optimization problems, we think about we get some graph, and now we want to find a point x where the function has large value. But there's in some sense a useful simpler problem to think about, which contains all the most of the algorithmic content of the optimization question. And this is so the decision version of the problem. And what does the decision version of this problem mean? So our goal is to compute an upper bound an upper bound C on the maximum value. And this upper bound should not be too far from the true maximum value. So we want a provable guarantee on how far our upper bound C is from the optimum value. Yeah, and this problem is in many cases a little bit simpler to think about. Okay. So now if you have this problem in mind, so how can we get a good upper bound for the maximum value of this function L sub g? So the idea is that we will try to decompose this function. It's a function on 2 to the n points. So we'll try to decompose it as in terms of constants and in terms of squares of linear polynomials. Okay, so what does it mean? So and this will turn out to be this will capture this meta-algorithm that's underlying the Nigam's conjecture. Okay, so what does it mean? We try to write the function L sub g as a constant c minus a sum of squares of linear polynomials f sub t. So now, if you can write, if you can decompose the objective function like that, it shows that that c is an upper bound on the maximum value that the function can take, just because these are squares, and so they take only non-negative values over the hypercube. And now, okay, and one important point here is that how should you think about this identity, this equality sign here? So one way to think about it is that it should be equal at every point on the hypercube. That's one way to think about it. But that sounds like a very inefficient way of checking this identity. But an equivalent way of checking this identity is just to go back to what we said before about multilinear representations for these functions. So because if you look at the left side, this is a degree 2 polynomial, and same thing here. This has degree 2. So it means in order to check whether these two functions are the same, we just need to check that the coefficients in the multilinear representation are the same. And so this means that the fact that you can check this identity by looking at the coefficients in the multilinear representation, it means that these functions f sub t are an efficient certificate that will prove that an upper bound on the maximum value of this function. Okay, and it also turns out that which I'm not sure if I say it somewhere else. It also turns out that you can find these functions f sub t efficiently. So if so there's an efficient algorithm for computing this number c, and also for computing the functions f sub t. And the reason is that I hope I think I write it somewhere else, but let me just say at this point. essentially the reason why you can do this efficiently is because if you have let's say a homogeneous quadratic polynomial, then you can write it as a sum of squares of linear forms, if and only if the coefficient matrix of the quadratic polynomial is positive semidefinite. So it means that finding this kind of polynomial is the same as finding a suitable positive semidefinite matrix. And you can check the membership problem for positive semidefinite matrices is something that you can solve efficiently. Okay, so this algorithm, if you apply it to MaxCut, it has a good approximation guarantee, which is the best known approximation guarantee for this problem. What does approximation guarantee mean? It means that the upper bound C that we compute in this way, it's always at least as large as the maximum value of the function, but it's never smaller. So it's always it's never much larger. So if you multiply our upper bound by 0.878, then it's also a lower bound on. Then this is a lower bound on the maximum value. And this is a result due to Gemens and Williams. Okay, so I think here is this remark about why you can solve it efficiently. So if you want to maybe just ask, in some sense, this we ask whether this function is contained in the set of functions in a set of functions that have this form, and this set of functions is a nice convex set, and the membership problem is equivalent to testing whether some matrix is positive semidefinite. So far, I explained it only for MaxCut, but maybe you can see that this is a rather general way of trying to get upper bounds on functions. And for example, if you have a problem where the alphabet size is larger, where there are not just two choices for every variable, but maybe there are q different choices for, that you can. Few different values that you can assign to a variable. And then instead of looking at the usual hypercube, we would look at this generalized hypercube. But everything else would stay exactly the same. And similarly, if our objective function would not be a quadratic polynomial like for MaxCut, but a degree 3 polynomial like for Max3sat, then we could basically use the same algorithm, except that you would also need to use sort of in these decompositions certain kind of Hund, in the case of Max3sat, certain kind of 3 Hundas. But it's like a technical detail, but essentially it's still the same algorithm. Another remark. So, in case you're wondering about the difference between solving a decision problem versus solving a search problem, it turns out that there's a generic scheme. So for this meta algorithm for the decision problem, there's a generic scheme to translate this to make this into a search algorithm, and the search algorithm will have exactly the same approximation guarantees as the decision algorithm. And, usually this kind of translation is difficult especially for approximation algorithms, but in this case it works. It works in a very general way, and it also turns out that the final search algorithm that you get in this way, it runs in quasi-linear time. Even though yes.
Excuse me, when you put this inequality here in the approximation guarantee, this 0.878 is like the inverse of the Grothendieck constant, or?
It's similar to the Grothendieck. I mean, you could write here the inverse of the Grothendieck constant if you wanted, and it's still a true inequality. But it turns out that this here is a bit larger.
It's correct, but works.
Yes. This is a bit larger. This is a bit better.
Because your objective function. Okay.
So yeah. Okay.
There's something positive semi-definite in the way you construct.
The reason why So this guy here is a sum of squares. So that's why it's a somewhat simpler polynomial than a general quadratic polynomial, and it's actually diagonally dominant, which also makes it a bit easier.
Okay.
But the nice thing is that we didn't have to know all these properties, that it's diagonally dominant or that it's positive semidefinite. We use this some sense for all these. You can use exactly the same algorithm, and you will get the right kind of guarantees. Okay, so this is the meta algorithm that the Unique Games conjecture predicts to be optimal. So now, the question is, investigating against conjecture true, or could there be an algorithm that is better than this meta algorithm? And so how could you try to improve this algorithm? And in some sense, I already described the algorithm in a way that is very suggestive for how you can try to improve it. So the general approach for how you can try to improve the algorithm is that you consider, instead of just squares of linear polynomials, you can try to consider a larger class of non-negative functions. But notice that we have to be careful with the kind of non-negative function that we consider. For example, if you would consider all all quadratic polynomials that are non-negative over the hypercube, this was actually would actually be NP hard to solve this. So somehow it's important that we use a simple class of non-negative functions. And simple means that in particular it's better if they are low degree, and there should be an efficient membership test. That's essentially what you need. And okay, and so the first kind of generalization that people tried is to look at non-negative functions that have a small number of influential coordinates. Okay, so non-negative functions that are juntas. And then, if you try to incorporate those kind of non-negative functions into the algorithm, what you would try to do is you would try to decompose the objective function as a constant, and a sum of squares of linear polynomials, and a sum of non-negative k juntas, let's say. And because there are not too many, because in some sense there are not too many k juntas, it turns out that you can still solve this problem efficiently. So if you look at k juntas, then you can solve it in time n to the k. And here there's a good sanity check. So so the claim is that so it's easy to see that if you choose k as equal to n, then this here would allow you to then you could compute the exact maximum value of the function over the hypercube. Okay. And the reason is that you would just you would just if c minus this L sub g is a non-negative function, it can depend on most n variables. Okay, so it means that this is a non-negative n junta. And now if you use if you choose one of the g sub s's, if you choose choose this to be 0 and choose just one of these g sub s's and choose it to be equal to c minus L sub g, then this identity is true, and you can do it up to exactly the maximum value of c. Okay, so if you would choose k as n, then you could solve the problem exactly. But notice that the running time would be exponential. So it's not an interesting. So from a computational complexity point of view, it's not interesting. Okay. So so the question is, are there upper bounds on the sizes of the juntas that you need that are much better than n? And it turns out that for this problem that we discussed before, for the small set expansion problem, it's enough to use juntas of size n to the epsilon. Okay. And this and this translates to an algorithm that solves this problem in time 2 to the n to the epsilon. And I will discuss in the next slide what's the implication of this kind of an algorithm for this problem. So it's quite rare for NP-hard problems to have this kind of algorithm. We also know that but we also know that. So now the question is, could you improve the bound on the junta size? But it turns out that any constant junta size does not work, in the sense that it doesn't give better guarantees than this basic semidefinite program that underlies that we discussed before. The simpler meta algorithm. And so it means that using these junta sizes, you can't get a polynomial time using these non-negative juntas. You can't get a polynomial time algorithm that refutes Sneak-Game's conjecture. Say again?
We know almost n to the epsilon, right?
Unfortunately not, because
Shortcode doesn't apply to this?
No, it does, but yeah, no, okay, that's the next point. So yes, so this proof, there's some. I think you can write some almost logarithmic Junta size now. But I mean, as Boas says, this proof it seems far from tight. In particular, there are constructions where it's plausible that you need Junta sizes Junta sizes that are almost polynomial, and under some assumptions about under some optimistic assumptions about the existence of locally testable codes, you could also get constructions of instances where you need almost n to the epsilon Junta sizes of almost n to the epsilon. So like here, this order 1 is a very, very pessimistic way of setting what we know. And so in some sense, what this means is with this with giving this kind of remark in mind is that you have pretty good understanding of what happens if you add these non-negative Juntas into the picture. Okay, if you enlarge the class of non-negative functions that you consider by these non-negative Juntas. So now let me discuss a little bit. What does it mean to have a 2 to the n to the epsilon algorithm for problems that are conjectured to be NP hard? So one point is that while it's there are NP hard problems that have 2 to the n to the epsilon time algorithms. It turns out that many NP hardness proofs they actually rule out these kind of algorithms. Okay, and in particular, if the reduction runs in nearly linear time or a fixed polynomial time, then they rule out these kind of algorithms. And so it means that that the existence of such an algorithm, it means that many kinds of NP hardness proofs don't work for these problems. And so that it means that it's it seems hard. So that means that certain approaches for proving the games conjecture are doomed to fail, just because there exists such an algorithm. It also turns out that if sort of a slightly if you would go beyond n to the epsilon and show a degree bound of n to the little of 1, which would mean this kind of an algorithm, that would actually that would be inconsistent with the usual kind of NP hardness, as assuming standard complexity assumptions. Okay, this line, and so there's an instructive picture that you can keep in mind. So if you look at a typical problem in this range, and you draw here the kind of approximation guarantees that you might want for this problem, and here you draw the kind of time complexity that you need in order to get this approximation guarantee. Then here we have a point which corresponds to the approximation guarantees that current algorithms achieve, and which also coincides with what the games conjecture predicts to be NP hard. Predicts to be the NP hardness threshold. And so up to this point, we know polynomial time algorithms. And then there's some point that coincides with what we know, with the currently known NP hardness results. And so at this point, because the NP hardness results are really of this type, it means that they show that the problem is NP hard, that getting these kind of approximation guarantees are NP hard. And now there's this region in the middle where we don't know yet what happens. And in some sense, there's this a priori you might there's this possibility that at the unigames hardness threshold, the complexity jumps from polynomial to exponential. And this is actually what happens for quite a few problems. But it turns out that like this, it doesn't happen generically, just because we know that there exists these 2 to the n to the epsilon kind of algorithms, for example, for small C expansion. So it means that for some problems, like the jump doesn't go immediately to exponential. And so if the games conjecture is true, the jump, there has to be sort of 2 jumps. One way it goes to some kind of 2 to the n to the epsilon complexity, and then there has to be sort of some transition to exponential complexity. So now let me explain a little bit what are the kind of mathematical what's the mathematical question that underlies these bounds, both the lower bounds and the upper bounds for for Hunter sizes that we discussed before. So it turns out that this is very, very strongly connected to the question about how eigenvalues relate to the expansion of small sets in graphs. So let me sort of explain this question. So let's define. So suppose you have a family of graphs G, and let's say it's a small set expander family. If there exists a positive constant delta, such that for all graphs in the family, satisfy that sets of that contain at most the delta fraction of the vertices, they have expansion at least 0.1. Okay? So there exists this, a family of graphs is a small set expander family if there exists this constant delta such that small enough, such that sets below this volume have non-trivial expansion, have significant expansion. And now the question is how fast can the number of small eigenvalues grow in graph families like that?
You're talking about eigenvalues of the Laplacian?
Yes, of the Laplacian. Yeah. And for example, okay, it's a sanity check question. So how many eigenvalues equal to 0 how fast can that number grow in a family like that?
1 over delta.
1 over delta, yes, exactly. If you have, if you have more than 1 over delta eigenvalues equal to 0, it means there's, a connected component of size at most delta times n, and that has a small expansion. So it means that, if you look at eigenvalues equal to 0, there's actually a uniform bound on the number of eigenvalues for all graphs in the family. Okay? But it turns out that if you choose the eigenvalue bound constant, then this uniform bound is false, and there are graphs that have a polylogarithmic number of eigenvalues at this point.
So maybe it's worthwhile to make sure that everyone got this. Or?
The previous point, or
In the eigenvalues of Laplacian, so right, Laplacian has positive eigenvalue value if and only if it's connected. So.
Right, or the number of 0 eigenvalues is equal to the number of connected components in the graph. And so if you have 1 over delta, more than 1 over delta eigenvalues equal to 0, it means one connected component has size less than delta fraction of the vertices. And that means that this graph in this family of graphs would not be a small set expander family. So it means that if you look at eigenvalues equal to 0, then there's a uniform bound for small set expander families. But if you look at eigenvalues below epsilon, they can grow with the number of vertices in the graphs. Okay, so n is the number of vertices in the graph. And it turns out that the degree bound, the bound on the Hunter sizes, it's captured by the following upper bound on the number of eigenvalues that small set expanders can have. It turns out that a small set expander can have at most n to the epsilon eigenvalues. So a family like that can have at most n to the order epsilon eigenvalues smaller than epsilon. Okay. But now there's sort of this big gap, this exponential gap between this lower bound and this upper bound. So it's a question, what's the truth? In particular, if this would have been the truth, it would have refuted the Niegam's at least this graph version of the Niegam's conjecture. But it turns out that there's a better lower bound, which almost comes close to this polynomial bound. And so there are families of graphs where the number of eigenvalues at most families of small set expanders where the number of eigenvalues grows like this, which you can think of quasi-polynomial from a lower bound perspective. And so in some sense this means that we have a pretty good understanding of so up to this gap between the upper bound and upper bound and the lower bound, we have a pretty good understanding of sort of what the eigenvalue distribution buys us in terms of algorithms for small set expansion. So now so now the question is, can we have something that is even more powerful than these Hunter sizes, or the number of eigenvalues in the graph, and that so that leads to these the sum of squares meta algorithm that we mentioned in the beginning. So the idea is that we are interested in simple classes of non-negative functions, and now we will just look at all polynomials that are sums of squares of low-degree polynomials.
I always get confused with this. You don't have to multiply the LG with anything, or it's.
So not because it's a finite set. You don't have to. It's just it's a little bit simpler if you do that. You can if you want, but you don't have to. And it turns out that it's still efficient, and the reason is that a polynomial is a sum of squares, if and only if you can sort of rearrange its coefficients into a matrix which is a positive semidefinite. And here rearrange has to be right in a careful way, but that's the basic thing that is going on. And okay, now the question is, does this improve the situation? And as we said, it turns out that it really improves the situation, at least for the kind of construction of instances that we know. In particular, the kind of graphs that we discussed before. It turns out that that if you add these squares of low-degree polynomials into the picture, then then the algorithm works. And so what's the underlying reason that the algorithm starts working if you add these squares of low-degree polynomials? So the underlying reason is that it turns out that sort of this step of adding sort of including here squares of low-degree polynomials, it corresponds to quite intuitive proof system that has very nice properties. In particular, you can do it's sort of invariant under changing the basis for your variables. So you can have a linear transformation of your variables, and like the proof system, it doesn't, it stays invariant under this basis change, which is very false for the proof system corresponding to juntas. And in particular, in this proof system captures sort of convenient facts like Cauchy-Schwarz and Hölder's inequality. And so it means that somehow like the proof system can use these things in order to come up with the upper bounds on the maximum value of these functions. And so one way to think about this proof system is that you're trying to prove some polynomial inequality over the hypercube, and you're allowed to use the usual kind of rules that you have for polynomials. If you have two inequalities, you can multiply them together, and it's still a true inequality. If you have if you can add them together, and it's still a true inequality. And you can use the axiom that a square of any low-degree polynomial is non-negative. Okay, so if you have a proof that uses only these kind of rules, and the intermediate steps only use low-degree polynomials, then you can also find the proof in this way efficiently. Okay, there's a small restriction. So you have to be careful with what it means that the intermediate steps only involve low-degree polynomials. In some sense, so for the purpose of measuring the degree in these intermediate steps, you should sort of think of the degree as symbolic. So it means that adding two, that if you add two polynomials, the degree doesn't go down, okay, even though maybe the leading term is constant. Just because otherwise this statement, the next statement is no longer true. Okay, but this it's something you can for intuition it's safe to ignore this small issue, and so it means that this proof system has this remarkable property that if there exists a small proof, then you can actually find it efficiently. Okay. Now the reason why this sum of squares meta algorithm works for these known constructors of instances is because you can now look at the real world proof that shows that these instances don't have a don't have a good solution. And you can lift this proof into this sum of squares proof system. And this works, surprisingly often. And in some sense, we never found, so far we haven't found a really convincing counterexample where sort of lifting a sort of real-world proof into the sum of squares proof system doesn't work. Okay. Now, so I want to describe a little bit more about sort of what's going on so in particular what's going on here in this part where you sort of want to lift some proof of some inequality into the sum of squares proof system.
So you have 3 minutes.
3 minutes? Okay, that's good. And it's good to, so it's instructive to look at the slightly different problem, which is the problem of finding sparse vectors in subspaces. So you're given a subspace, and your question is, and the goal is to find a sparse vector in the subspace. Okay. And this turns out to be closely related to the small cell expansion problem, because the reason is that if you sparse non-expanding sets, they correspond to small non-expanding sets in the graph. They correspond to sparse vectors in the span of the top eigenvectors of the Laplacian. But it turns out that this problem also has connections to a wide variety of problems, and John will talk about this problem in detail in the next talk. But so let me just mention here that it turns out that for many interesting linear subspaces, in particular the kind of linear subspaces that arise in these constructions, it turns out that there's a way to certify that the subspace doesn't contain sparse vectors using this sum of squares proof system and using this sum of squares meta algorithm. Okay, and how does the certificate look like? The certificate looks as follows. So it's a certificate says that you can write this function. So think of this as a function in ranging over. If you range over U, you can write it as you can write it in this way, and this means that because this here is always non-negative, this means that the 4 norm to the 4 is bounded by 1 over n times the 2 norm to the 4. And now, if you think about what it means, is that if you have a very sparse vector U, say it has puts all its mass on one coordinate, then the 4 norm to the 4 would be the same as the 2 norm to the 4, and so it means that if the 4 norm to the 4 is much smaller than the 2 norm to the 4, it's 1 over n factor smaller than the 2 norm over to the 4, it means that this vector is sort of spread out across all coordinates. So it means that it's very non-sparse. It's sort of almost fully dense vector. And this identity, it's a certificate that the subspace doesn't so that all vectors in the subspace are of this are completely spread out. And one remarkable thing is that usually people think about try to reason about sparsity in terms of L1 norms, and this is something that would fail quite badly in this case, because if you try to relate the 1 norm, let's say, to the 2 norm, then this would not be a polynomial. So like this identity would not be not a low degree identity, and it would not correspond to something that you can check efficiently. So now, okay, let me in the last minute explain a little bit. So far we sort of only saw that the sum of squares meta algorithm it works well on particular instances. If you know either exactly what's the distribution that generated the instance, or how the instance was constructed. So now a question, but ultimately we want to use this meta algorithm to sort of prove better guarantees also for worst case kind of problems. And here there's sort of a basic issue that what we try to prove is something of the following form. We want to prove that if the sum of squares meta algorithm cannot rule out a solution with large value, then you want to be able to find a solution that has reasonably large value. Again, there's a sort of an awkward mismatch of the quantifiers. Okay, because the question is how could we use the non-existence of a certificate in order to find a good solution? And here is really what saves us is convex duality and the algorithmic version of convex duality, which says that if you fail a certificate, if you fail to find a certificate of this type, then you can actually find an obstruction, and the obstructions in this case okay. So what is so if you have I guess. So it turns out that what is an obstruction for finding a proof that what is like a canonical kind of obstruction for finding a proof that there's no that the function doesn't take a large value. A canonical obstruction is there just there exists a point where the function has a large value. Okay, but now. In this setting of convexity, you can also have obstructions that are convex combinations of such single points, and that so of course wants to having distributions over points where the function takes large value. And it turns out that in some sense all obstructions that arise in this way, you can think of them exactly like distributions over points where the function takes large value. Okay. And in the formal sense in which you can think of the abstraction in this way is that the abstraction that you find is indistinguishable from a distribution with respect to the kind of tests that you can generate by the sum of squares proof system. And this leads to this notion of a pseudo distribution. And let me. So here's the definition of a pseudo distribution. Let me skip this. You can find it efficiently. So that's a useful thing. And now the approach is that if you want to use it to construct an algorithm, the approach is that you think of an algorithm that gets as an input this this object that looks like a distribution over optimal solutions, and you try and the algorithm tries to extract from this object an approximate solution to the original problem. And it turns out that unless this algorithm, as long as this algorithm doesn't use, so suppose this this algorithm runs in some fixed polynomial time, then it's a very good heuristic to analyze the algorithm first, for the case where you give it an actual distribution over optimal solutions as input. And so there's you can think of it as a heuristic algorithm design paradigm where you first analyze these kind of algorithms, assuming that they get this kind of a distribution as an input, and then later you check that the properties that you used about these kind of distributions, they are captured by the sum of squares proof system, and that would mean that the algorithm also works if you run it on these pseudo distributions, which is actually something that you can compute. Okay, I think I'm over time, so let me conclude. Thanks a lot.